So in this video, we'll be covering the topic of source transformations as they apply to AC, DC, and dependent sources. So first thing we're going to do is explain what they are. Then we're going to explain why we need to use them. And then we're going to give some examples. So let's look at why we would potentially want to use source transformations. So if we look at the circuit below, you'll notice that using methods of node voltage or mesh current or any of the other tools you've learned about how to solve circuits up to this point, it wouldn't be very easy. So that's why we're going to introduce source transformations, because this circuit analysis becomes much simpler when you have that.
So what are source transformations? Primarily, they allow us to change from a voltage source with a resistor in series to a current source with a resistor in parallel across two terminals A and B. To transfer between the two, we use Ohm's law in the following form, where the voltage source is equivalent to the current source times R, the resistance. So why does this work? Well, if you put a load across the terminals A and B in both circumstances, we can use Ohm's law and voltage divider and current divider equations to get the following four sets of equations. So Ohm's law gives us this equation and this equation, voltage divider and current divider, by examining the following two circuits, right? All these equations are only equivalent whenever Vs equals Is times R, or the transformation equation we used up here. To see this, you can plug in ISR to this current equation here, and you get this equation over here. You can do the same thing with this voltage equation here, and you get the equation over here. Therefore, these transformations are valid, and they allow us to greatly simplify circuits. So why doesn't the other form work, where you have a current source with a resistor in series and a voltage source with a resistor in parallel? Well, other than the fact that the equations with the load across that we just saw wouldn't work, this circuit will have the same current regardless of this value of R. And this circuit will have the same voltage across terminals A and B regardless of the value of the resistor R as well. Basically, the resistor merely draws power in these circuits, so there's no valid transformation between the two.
Okay, so this is the circuit that we showed on the very first slide of this video. And we can go ahead and analyze the circuit, and what we're looking for is the voltage across this 28 kilo ohm resistor, and we're going to call that V0. So now that we know about source transformations, this circuit becomes much more simple to analyze. So we have, if we look over here, we have this 8 milliamp source in parallel with this 5 kilo ohm resistor, which can then be transformed into an equivalent voltage source here of 40 volts, and that would be in series with a 5 kilo ohm resistor. And then I already went ahead and did the series combination of the 5 kilo ohm resistor with a 10 kilo ohm resistor to get the 15 kilo ohm resistor. And then we have these two voltage sources which are also in series. So we can go ahead and add those together because their polarities are the same, and we get 75 volts. And then that is in series with this 15 kilo ohm resistor. But then this is a configuration that we can then transform into a current source again, and we get back to a 5 milliamp source current, and we stick that in parallel with this 15 kilo ohm resistor. But then we notice that that is in turn parallel with this 30 kilo ohm resistor, and we can do a parallel combination of 15 kilo ohms and 30 kilo ohms and rewrite this circuit, and we get an equivalent resistor of 10 kilo ohms. But then you see again that this 5 milliamp source and this 10 kilo ohm resistor can be transformed into a voltage source of 50 volts, and that would be in series with this 10 kilo ohm resistor. But then these two are in series as well, so we can add them together to get 25 kilo ohms, and then transform the 25 kilo ohms with the 50 volt source into a current source in parallel with that 25 kilo ohm resistor, and we get 2 milliamps as our source current. But we notice that that is in parallel with this 1 milliamp current, and we can treat them much like you would treat resistors in series, so we can just add them together. But since this is going down and this one's going up, we can say it's a net total current of 1 milliamp going up. We can redraw the circuit. So we get our source is 1 milliamp going up, and then we can transform the 1 milliamp in parallel with 25 kilo ohms over here into a 25 volt source, in series with this 25 kilo ohm resistor. And then we can directly solve for V0 using a voltage divider, and we get 13.2 volts.
Now let's look at an example where we use source transformations with dependent sources. So let's start off with a warning. The element which has the control voltage or current for the dependent source must not be changed. Otherwise, the dependent source will also change and the circuit is not valid, and it's not a valid transformation. So we have to conserve that element. So let's look at the following circuit. Here, that element with the control voltage is right here, this Vx. We have a voltage-dependent voltage source over here that's dependent on that Vx. Right? So let's examine this circuit and find the voltage across Vx. Now there's multiple ways to do this, but one valid way and one simple way is through source transformations. So we can see here that this resistor is in series with this dependent source. So using the following equations here, we could find that this transformation is valid. We now have the current source being Vx over 3, and the 6 ohm resistor is now in parallel with the current. These of course can be combined to form a 3 ohm resistor, and then we could change this now back to a voltage dependent source using the following equations, right? So now we have the 3 ohm resistors in series with this voltage source, which is simply just Vx. So now we have a simple to examine circuit which can help us find the voltage across this resistor, or Vx. So we examine the current through the whole thing. We can see it's equivalent to 12 minus Vx over the total of the two resistances, so 6 ohms. Now that we have the current, we can use Ohm's law to find Vx. So I times R equals 12 minus Vx over 6 times 3, which is 12 minus Vx over 2. And then through some simple algebra, we could see that Vx is 4 volts. So that's a very simple way to examine a circuit that has a dependent source, which is sometimes an annoying circuit to deal with. And all we have to do is 2 simple transformations and some parallel series combinations.
Okay, so a little disclaimer before we get started. We are going to cover AC transformations. So if you haven't gotten to this part of the course yet, which you most likely haven't if you're looking at this video now, then it's just going to be really confusing. So don't look at it if you haven't covered AC circuits yet. But if you're taking a look after having learned about AC circuits, then by all means go ahead, and this might be just kind of a good review of how to do source transformations and see how exactly they're applied to AC circuits. Okay, let's get started. So we are looking for the Thevenin equivalent circuit of this circuit below. So you'll notice that there's an inductor, capacitor, and resistor, all with their phasor domain values given, so that we don't have to worry about converting back to Cartesian or doing anything like that, and we can just we can basically treat everything as though it's a resistor. So let's get into it. So you'll notice at first that we have this inductor and this capacitor, that they are in series. So we can do a series combination, and you'll see that 60J minus 48J is 12J. So we can replace these two with an equivalent black box impedance of 12J. And then you can notice that we can do source transformation here, and we can take this to a current source in parallel with that impedance. So you'll see that we get 240 divided by 12J, Ohm's law, is equal to negative 20J, and that's our current source. And we stick that in parallel with the 12J impedance, and you'll notice that we can do a parallel combination of 36 and 12J. And when we do the math, we get 3.6 plus 10.8J, and here's how you do that again. And it's just as though it's just the same as if they were both resistors, just using their component values. But then we can also do a source transformation back into a voltage source. So let's do that. So when we do Ohm's law again, we get a 216 minus 72J voltage source, and we use this same impedance here, and that is indeed our answer for the Thevenin equivalent across the terminals A and B.